Here's an alternate way of doing this problem 2834. In the figure at t equals 0, the switch S is closed, capacitor is uncharged. If C is equal to 40 microfarads, EMF of the battery is 50 volts, and R is equal to 5 kiloohms, how much energy is stored by the capacitor when I is equal to 2 milliamps? Energy stored in a capacitor is 1/2 CV squared. So if we could find the voltage of the capacitor when the current is 2 milliamps, we could find the energy stored. Well, we know this is a DC circuit, and the EMF of the battery is 50 volts. So that 50 volts is being shared by the resistor and the capacitor. If we could find the voltage across the resistor, we could then find the voltage across the capacitor. So that's our alternate method. Voltage across the resistor is equal to the current times the resistance according to Ohm's law. And at 2 milliamps, that's a current of 2 milliamps times a resistance of 5 kiloohms. 10 to the minus 3 and 10 to the 3 cancel out. And this is 10 volts. So that's the voltage across the resistor. Hence, the voltage across the capacitor is the EMF of the battery minus the voltage across the resistor. That will be 50 volts minus 10 volts, or 40 volts. So when the current is equal to 2 milliamps, we have 40 volts across the capacitor. Now the energy stored by that capacitor is 1/2 CV squared. So that's 1/2 times the capacitance, which is 40 microfarads, times 40 volts squared. And that is equal to 32,000 microjoules. Or we could write that as 32 millijoules. So that's the energy stored in the capacitor when the current is 2 milliamps, 32 millijoules. It's an alternate way of doing this problem. It doesn't really involve any real knowledge of RC circuits except for the energy stored in a capacitor. And it's using our knowledge of DC circuits and Kirchhoff's voltage rule. But it's a shortcut we can possibly use if we're lucky enough to know this information about the current.